In this video, we are going to solve some optimization problems. These are problems that apply the concept of critical points, therefore they involve maximum or minimum quantities, whichever is applicable, whichever will give the best results, or whichever is beneficial for the given scenario or the given problem. So problems like maximizing the profit while minimizing the cost, or let's say we have a fixed amount of material and we want to construct or we want to make something like a box with a maximum volume, those kinds of problems. To solve optimization problems, we have some guidelines. Number one, if possible, provide or make a sketch, especially if geometric figures are involved. This will give us a clear view of what we are dealing with, and so that we can relate the unknown quantities to the known quantities easily. Next, we need to set up the primary equation. This is the equation for the quantity that we need to maximize or minimize. In other words, this equation is the equation to be differentiated. Now, most of the time, the primary equation is defined in terms of more than one independent variable. So, we'll be using the given constraints in the problem to formulate secondary equations that will help us reduce the primary equation in terms of a single independent variable. After the primary equation is reduced in terms of a single independent variable, we can now differentiate the resulting equation and equate it to 0. This is done in order to find the critical values of the equation, which are either a maximum or a minimum value. Lastly, we can check if the critical values are a maximum or a minimum using the first derivative test or the second derivative test. Now let's solve some problems. Number 1. Find two non-negative numbers whose sum is 9, and so that the product of one number and the square of the other is a maximum. We can define the first number as x and the other number as y. The sum of x and y is 9, so we have our first equation. The product, let's denote the product as p of one number, let's say that's x, and the square of the other, so that's y squared, is a maximum. So x y squared is equal to p. We have formulated two equations. The question now is which of the two is the primary equation and which is the secondary equation. So going back to the problem, it is stated that the product is a maximum, meaning the product should be maximized. The equation for the product is the equation that we need to differentiate. Therefore, this is our primary equation. Then we are required to find the two non-negative numbers, x and y, if p is a maximum. To start the solution, let's take the primary equation, p equal to x y squared, and notice that it is defined in terms of two independent variables, x and y. This is now where we use the secondary equation, which is x plus y equal to 9. Since x plus y equals 9, then we can either isolate x or y say we isolate x, so we get 9 minus y. Then we'll plug in this equivalent expression for x to the primary equation. Okay, so again, our primary equation is p equal to xy squared, and since x is equal to 9 minus y, we can write our primary equation as 9y squared minus y cubed. The primary equation is now in terms of a single independent variable, so we can now differentiate this equation. Differentiating p with respect to y, that's 18y minus 3y squared. Next, set this equation to 0. We can factor out 3y, right? So that we are left with 6 minus y. This will give us two solutions: 3y equal to 0, 6 minus y equal to 0. And so we get two critical values, y equal to 0 and y equal to 6. We can solve for the corresponding x values using the secondary equation, x plus y equal to 9. And then after we solve for x, we can solve for the product using the equation p equal to x y squared. So if y is equal to 0, plug in y equals 0 into this equation, x plus y equal to 9, we get x equal to 9. If y is equal to 6, then x is equal to 3. So let's solve for the p values or the product. For y equals 0 and x equals 9, the product is, so 9 times 0 squared, that's 0. And for y equals 6 and x equals 3, the product is 3 times 6 squared, so that's 108. Since we want a maximum product, looking at the values of the product, this set of x and y values makes sense for the problem. Therefore, we can say that y equals 6 and x equals 3 are the values that we are looking for. We can also use the first derivative test to check the answer. So what we want to know if there is a change in the sign of the first derivative going from the left of the critical value to the right of the critical value. So the first derivative that we obtained earlier is dp dy equal to 18y minus 3y squared. So 18y minus 3y squared. And the critical values are y equal to 0 and y equal to 6. So let's test. Let's draw a number line. Let's say this is y equals 0. Let's choose some test values on the left and on the right of y equals 0. Let's say on the left -1, on the right +1. Now if we plug in -1, we get a negative value. Therefore it's a negative slope. The function is decreasing, right? If we plug in +1, we get a positive value. The slope is positive, therefore the function is increasing, right? If this is the case, then we have a minimum at y equals 0. Now let's check for y equals 6. Let's say this is y equals 6. On the left we can use 5. On the right we can use 7. Let's plug in 5 to the equation of the first derivative. We'll get a positive value, a positive slope, so the function is increasing. And then if we plug in positive 7, we'll get a negative value. This means it's a negative slope, so the function is decreasing. If this is the case, then we have a maximum at y equal to 6. So this will give us a maximum product. We can also use the second derivative test. What we need here is the second derivative. So second derivative of p with respect to y equals, so 18 minus 6y. And then we plug in the two critical values, y equals 0 and y equals 6, and check for the sign of the second derivative, right? So if we plug in 0 to the second derivative, we get a positive value. If we plug in 6, we get a negative value. If the sign of the second derivative is positive, therefore it's concave upward, right? If it's concave upward, then the critical value is a minimum. Now if the sign of the second derivative is negative, it's concave downward, and so the critical value is a maximum. Therefore y equals 6 will give a maximum product. Problem number 2. 500 feet of fencing material is used to enclose a rectangular field with a building on one side of the field. Determine the dimensions of the field that will enclose the largest area. Let's say this is the building and this is the rectangular field. So we only need to fence these sides of the rectangular field because we have a building on one side. Let's call this side y. If this is y, this is also y. And then the longer side, let's call it x. And then we want the largest area possible. Therefore, the primary equation is the equation for the area of the rectangle, and that's the length times the width, or in this case, x times y. Then we are required to find the dimensions, x and y, at maximum area. Again, the equation for the area is our primary equation. Let's solve. So we have the primary equation, a equal to the product of x and y. We can either define this equation in terms of only x or only y using this equation. Let's say we isolate x from this equation. So x equals 500 minus 2y, and plug in this equivalent expression to the equation for the area. So the area now is equal to 500 minus 2y times y, or this is equivalent to 500y minus 2y squared. taking the derivative with respect to y, we get 500 minus 4y. And then setting this equation to 0, we get 500 minus 4y. If we transpose 4y, we get 4y equal to 500. And then divide both sides by 4. So we get y equal to 500 divided by 4, that's 125. This is in feet. We can now solve for x. X is 500 minus 2y, where y is 125. Therefore, x is equal to 250 feet. So these are now the dimensions of the rectangular field with a maximum or largest area for 500 feet of fencing material.